Hi, welcome back. In this video, we're just going to look at many different types of examples working with the discrete time and the continuous time impulse and step. So it's kind of like a buffet today. Lots of different things going on. Okay, so first let me give you an example of using the sifting property in discrete time. So let's say we have a signal xn, and let's say xn is defined as 1/2 n minus 1 when n is greater than or equal to -2 and 0 else. So you can actually use the unit step to characterize the signal more compactly, but we'll just write it like that. And let's suppose that I want to evaluate the following sum. Let's say I want the sum of delta of n times x of n. N goes from -infinity to +infinity. Okay, and I'm just going to write the sifting property again here for you. This is n equals a to b of delta of n minus k x of n equals x of k if k is between a and b, and 0 else. Okay, this was the sifting property we saw, I believe, in video 1.14. Okay, so here's the example 1 we'll call it. And we compare the left of this equation sifting property to what we have here, and they look very similar. A is -infinity, b is infinity, xn is this signal here, and k is 0 because we're subtracting 0 from the impulse argument. So I can apply the sifting property, and we'll ask ourselves, well, does k fall between a and b? So k is 0 in our example, and a is -infinity and b is infinity, so of course 0 falls between -infinity and +infinity, so yes. So the top part of this solution applies. So our answer is x of k, x of 0. So this gives me x of 0. So what's x of 0? Well, here's my signal over here, and I plug in 0 for n. So 0 is greater than or equal to -2. So what do I get when I plug in x of 0? I get 1/2 to the -1. Or 2. 2 is the answer there. Okay, let me give you another example, similar, related. Let's keep the same signal, but let's sum from 1 to infinity of delta of n x of n. So it's very similar, but the bounds have changed. So now, observe the sifting property. K is still 0 because we're shifting the impulse by 0. Does 0 fall between a and b? No, 0 does not fall between 1, a is 1 now, and infinity. So the answer to this is 0. Okay, let me give you a third related example. N goes from 1 to infinity of delta of n minus 2 x of n. Okay, now we compare this to the sifting property, and we see that k is 2 this time, right? And we ask ourselves, does 2 fall in this range of summation, 1 to infinity? Yes. So the answer to this is x of 2. So we need to evaluate our signal at the value 2. So 2 is greater than or equal to -2, so we plug 2 in here, and we get 1/2 to the 2 minus 1, or just 1/2. And that's our answer. Okay, so that's the discrete time sifting property. Now I want to look at another example. Let's say we had a signal that looks like this. This is not going to be a sifting property, but this is just an example using the impulse. So let's say the height of that is 4, and then it comes down to 3. Okay, and then we have zeros from here on out. And we have zeros this way. Okay, so that's our simple signal. I call that x of n. Okay, so this is a different x of n. Maybe I should have called it g of n. I should call it g of n because it's a different example now. We're moving on. So we'll call that g of n. And the question is, can you write g of n as in terms of impulses? So write g of n in terms of impulses. That's the question, right? So we want to write a mathematical function for g of n. G of n equals what? Okay, well, I have to put some bounds or some axes here. We'll say the origin is there, -1, 1, 2. Okay, well, I want to write it in terms of impulses. An impulse looks like this. 1 at the origin. Right? This is the impulse. Well, if I take 4 times an impulse, then 4 times all zeros gives me 0. And then I'll have a 4 at the origin. So 4 times the impulse will look like this. So that's a good start because I have a 4 at the origin. And if I add to that, let's say I advance that signal by 1 unit. Okay, so what's the mathematical equation for, or representation of an advancement? N plus 1. So this is now 4 of delta of n plus 1. And you see, if I add those two things together, I'm adding mostly zeros. So I'll have 0, 0. Then I'll have a spike at -1 and at 0, right? That go up to 4. Then I'll have zeros. And that's an even better start, right? Because I have, if I look at my original signal, I have a 4 at -1 and a 4 at 0. So I could continue on like this. And I can write my function or my signal as 4 delta of n plus 1 plus 4 delta of n plus 4 delta of n minus 1, so that's the delayed impulse, that's this one here, plus 3 delta of n minus 2. Okay, that's it. So let's say we wanted the same example, but instead of impulses, how about unit step? Okay, so we're going to repeat this and we're going to write it g of n in terms of the unit step. Okay, well the unit step, remember, I'll erase some over here. The unit step in discrete time looks like this. It's 1 towards infinity, and it's 0 towards negative infinity. This is the unit step. Okay, well, if I look at my original signal, g of n, I have zeros until -1, and then it shoots up. So that kind of looks like a unit step, except we have to advance the unit step by 1 unit. because the jumping up occurs at -1 and not 0. So we advance it 1 unit, and we scale it by 4 because it goes up by 4, not 1. So a good start to this would be 4u of n plus 1. Okay, so that signal will look like this. Here's 4 now. So this is 4u of n plus 1. So that's not exactly what we have. We have now at 2, so it stays 4, which is good, right? This is -1, 0, 1. But at 2, I need to jump down to 3. So what I'm going to do here then is subtract. Subtract because it goes down a unit step, delayed by 2 units. So let's think about what that would look like. U of n minus 2 would be like this. This is 1, and this is 2 here. So if I subtract u of n minus 2 from 4u of n plus 1, so if I do this subtraction, then I would have 4, 4, 4, and then at 2 I would have 4 minus 1 is 3. And then I would have 3's from here on out, you see. So that's closer. And then finally I have a jump at 3. I go back down to 0, so I have to subtract. My jump goes from 3 to 0, so I have to subtract 3 unit step delayed by 3 units. And that is our answer. So both of these things in the box are the same mathematically, but they're just different representations. All right, let me erase this. Feel free to pause the video, go back. All right, let's look at another example. If you didn't quite get that, I've got kind of a similar example coming up next. Let's call this x of n. And let's say 0, 1, 2, and then a 1, 1, 1, 1, like this. So that's at 3. And then let's say we've got -1, -1, -1, like this. And this is -1. Okay, so there's our signal, and we're going to represent x of n in terms of impulses and unit steps, just like we did in the previous problem. Okay, so what I can do is just look at the left half first. So I'm going to work with impulses first. And the left half is an infinite number of impulses, right? Because this goes from -1 all the way to -infinity. So I can add a bunch of an infinite number of delayed, or advanced, I guess, advanced impulses. So I can start with the left side of this, and I can say, I'm going to add up, k goes from -infinity to -1 of delta of n minus k. Okay, so think about what that is, and whenever we write something in sigma notation like this, you can just start plugging in values of k to try to get an idea of what's going on. So if we did that, so let's say k is equal to -3. So this would be delta of n plus 3, and then the -2, delta of n plus 2, and the delta of n minus 1, or n plus 1, excuse me, the -1 term. So these are impulses that are advanced by 3 units, 2 units, 1 unit. Oh, we need a negative sign here. So this turns into minus minus, minus. So these are inverted impulses. So they go down by -1 at advance by 3 units. So that would be this guy. Advance by 2 units, that'd be this guy. Advance by 1 unit, that'd be this guy. And of course these go on for infinite. K goes from infinity, so that covers all of these to the left. Then we have a similar thing at the right. So we're going to add, because these impulses are positive, we're going to add K goes from 3 to infinity of delta of n minus K. And that's our answer. So this is the mathematical representation of this signal x of n. Now let's try to do the same thing, but with unit impulses. Excuse me, unit steps. We just did impulses. Okay, well, hopefully you're catching on now. And so we'll see, we have a jump. Actually, this one I guess is a little bit trickier. Remember that the unit step looks like this. Okay, this is the unit step. And so how are we going to nail out this first part, this left part? Well, notice we need to flip the unit step first. So we're going to flip it. And then we're going to advance it by 1 unit, like that. So that way, when we do that, the u of minus n minus 1 looks like this. Okay, that's the flipping part. And then the advancing part means this edge goes at -1 instead of 0. So this is u of minus n minus 1. And if we make that negative, then this becomes -1 instead of 1. And that's what we have in our original signal. Okay, then we need to add to that this is a regular old unit step, but delayed by 3 units. Okay, and that's our answer. That's it. All right, let's move on to the continuous time. Okay, let's say we wanted to evaluate this integral. How about minus infinity to infinity of delta of t e to the j omega t dt. Okay, and I'll remind you of the sifting property of the continuous time impulse. It says this: the integral from a to b of delta of t minus tau x of t, excuse me, dt equals x of tau, if tau is between a and b, 0 else. Okay, so that was our sifting property in continuous time. So we compare that now to our integral that we have here, and we see that tau is 0. Okay, tau is 0, and we ask ourselves, does 0 fall between a and b? A is minus infinity, b is infinity. So yes, of course 0 falls between minus infinity and plus infinity. So this top portion applies, and so we get x of 0. But what is x? X is this function here. Okay, so let's step back a little bit and let's just form fit this. A, by just comparison, a is minus infinity, b is infinity, tau is 0, and x of t is e to the j omega t, right? Compare those things. All right, so as we were saying, tau does fall between a and b, so this is x of tau. So this integral is x of tau, x of 0. And so what do I get when I plug in 0 for t here? I get e to the 0, which is 1. So that integral is 1. Let's suppose I had something like this. Okay. So here, I make this kind of the same comparison. I try to form fit this to the sifting property, and I see that nothing has changed except that tau is 2. So this is x of 2. So that's e to the j2 omega. That's the answer. All right, what if we change the bounds, maybe 3 to infinity? Okay, well, tau is still 2, but now 2 does not fall between the bounds of integration, 3 to infinity. So the bottom portion of the sifting property applies. So this integral is 0. Okay, so I hope you get the idea there. Now, let's look at how to use the unit step. Or let's investigate that. Okay, let's say we had a function or a signal that looks like this, with a slope of 1 over here and a slope of -1 over here. And this was our signal x of t. Okay, and the question is, express x of t, and of course this signal is the absolute value of t, in terms of the unit step. Okay, that's what we're trying to do. All right, so let's just worry about the positive values of t for right now, this line here, sloping upward. So the equation of that line, you should know from algebra, is x equals t. Okay, so we're going to write x of t equals t, but that only applies for positive values of t. So we're going to put a unit step there. We're going to put a unit step. So let's think about what, and we're not done yet, but let's think about what this signal would look like right now. For negative values of t, the unit step is 0. So I would have zeros. And then for positive values of t, the unit step is 1, and then I have this line. Okay, so that's what I've got so far. And what I'm going to do is add to it, or I guess subtract, because this line now is x equals negative t. So I'm going to write negative t, and I'm going to multiply that by a time-reversed unit step. Right? Because now for negative values of time, this unit step is going to be 1. And so this, this term takes over now, because this term is 0 for negative values of time. So now I've got the negative t line. then when t becomes positive, this unit step is 0, and this guy becomes non-zero, and so I've got this part. And so this is a compact way of expressing the absolute value function, right? A piecewise function. Okay, let's look at one more. Call this g of t. And we'll say this edge goes up at 1 and comes back down at 2. And we want to express g of t in terms of the unit step. Okay, this is a signal that you would see in digital electronics. Maybe a 0 and then a 1 and then back to 0. All right, so mathematically we're going to model that with the unit step. Well, I'm at 0 and then I have a jump at t equals 1. And so that is a delayed unit step, like that. So now I'm at 1, but now I need to switch back to 0. So that is another unit step, okay, at 2, so delayed by 2 units, but we're jumping down, so we're going to subtract, and we're jumping down 1 unit. So we subtract the unit step, but delayed by 2. And that's it. Now, I do want to throw another example out there. We're calling this g of t. Let's consider the derivative of g of t with respect to time. Okay, so this is a related example. Let's think about what that signal would look like. Well, the derivative is the slope of the line. So I've got 0 slope everywhere except at these jumps, right? Except at these jumps. So at 1, I have an instantaneous jump to 1 unit. So that's exactly an impulse. And it has to integrate to 1 because I pick up 1 unit of area. And then at 2, right, then I have 0 slope. And then at 2, I have a jump down. And then I have 0 slope again. And this has to integrate to -1 because if I'm accumulating the area, I have to get back to 0. Okay, so here's the derivative of this signal here, g of t. So how can we write a mathematical expression for that derivative? Well, yeah, we use the impulse. So this is at 1 and this is at 2. So this is the impulse delayed by 1 unit. Then minus, because the next impulse goes down, minus the impulse delayed by 2 units.